Hi, so please be seated. I want to start. Okay. I'm Hagit Grushka, Cohen, and I am a PhD student at Ben-Gurion University. And I'm going to tell you today about a research that I've done in collaboration with IBM Cyber Centers of Excellence and with their, especially for the product Guardium. All I'm telling you about today is already incorporated into their product, so it's something that really is working. So I want to start my talk by giving you 244 million reasons why you should monitor your data. Well, I don't know how many of you have heard about the story about Waymo and Uber, so I'll just tell you about it. Well, let's say that you're a self-driving car, self-automated driving car company, and that your leading engineer decides to leave the company and go to work and decides to leave, but he leaves not before he's downloading the entire database, the entire spec, that is 10 gigas of data, everything you have, all the patents, all your interesting stuff. And he takes it and goes with the disk on key to your biggest competitor, Uber, and offers them the data. Well, imagine how pissed you'll be, right? Well, I don't know if you haven't heard about it, then I really recommend reading. It's maybe 4 solid chapters of The Good Wife, if not the whole entire season. Well, so luckily for Google or Waymo, they were monitoring their data. And they sued Uber for stealing the data. And because they were monitoring their data, they had the proof that the data was used, so they had the entire story was about not whether this data was stolen or not, but whether it was used or not, which led to only after 6 days of... So only after 6 days of trial to a $244 million settlement. $244 million settlement. I bet that Google were pretty happy about their ROI from the database activity monitoring investment. So now that you're all convinced that you should monitor your data, so let's talk about how you do it. So what is a database activity monitoring? Just like in the criminal justice law, that the people are represented by 2 separate yet equal important parts, we have here the collectors and the anomaly detection. The collector is an agent that sits and that all the data goes through, all the queries go through. And this data that is collected is going into the anomaly detection, which identifies anomalous activities within the data that was collected. So we have big data, all the queries, all the database being fed into the anomaly detection, which in turn fires alert to the security officer. And today I'm going to focus about the challenge of how do we rank these alerts and why should we rank these alerts. So the main user of our system is the security officer, right? The expert. He's the expert. He knows what's important. He's in charge of keeping our organization safe. And the anomaly detection fires many, many alerts, mostly false positives. And we would like to prioritize them so that they will show him first the interesting stuff and only afterwards the less relevant stuff. So we actually want to make the system be more approachable and more useful for our users so that he will not be swamped with all these non-interesting alerts, missing the interesting stuff. So how do we do that? How do we prioritize it for him? We would like to assign a score for each activity or each alert, each transaction, right? And we ask ourselves, can we prioritize it? If we will, as I said, if we prioritize the alerts, we can reduce the amount of alerts that are swamping the security officer, and we will improve the adoption of our system. So let's talk a little bit about how do we assign a risk score. I want you to get the feeling and to know that it's a hard job. So we have here 3 users. We have Alice, she's an analyst and she's in the sensitive user group. She's querying a sensitive database of ours. We have Bob, who is in procurement, and he's not a member of the sensitive user group, but currently he's querying sensitive database of ours. And we have Eve. She's at HR, and she's in the sensitive users group, of course, and she's querying all the finance database during the working hours. So, I don't know, let's talk about Bob. Which score should we give him, this activity? Is it a 7? Who here thinks it's a 7? Who here thinks it's a 4? Raise your hand. Who here thinks it's, I don't know, a 5? So assigning a score, it's really hard, right? But if I would ask you to say which activity is riskier, carries more risk, that it would be easier. And if I'll ask you to do it pairwise, just like ignore Alice and compare Bob and Eve, it will be even much easier job. So my objectives, or our objectives in this research, were to enable a single score in order to prioritize alerts. I'll show you later on that this number has more uses, and it can also be used as a prior for sampling. And we want it to be a feature-agnostic solution. And we wanted to provide useful results from the beginning, out of the box, because we don't want to come to our customers and tell them, you have to do a lot of work to make this system work. And we wanted to improve over time, to learn and to evolve with our users and with these needs. And we want it to be explainable. I don't really need to explain why it should be explainable after such a day. And also, in the security domain, we have this problem that the policy constantly changed. It's not constant. The risks, the malware, everything is very dynamic, so we wanted to learn. And also, sometimes, from time to time, we get new orders for what we should monitor from the government, from the IRS, etc. And we need to monitor it. So we want the user to be able to manually calibrate it, that it will monitor this data. Okay, so we understand the problem. Let's discuss solutions or approaches for a solution. For, I say, prioritizing our alerts and eventually giving them scores. So one option is to use analytic hierarchy process, or what I call AHP. It comes from the domain of knowledge representation. And it's a heuristic that once we know the features that our problem is made of, so once we know the features, we can ask the security expert to prioritize between pairs of features, which is more interesting than the other. Let's say, what is more risky? The time of the day that we're approaching of the query, or the location that the query was made of? What type of data is it? What type versus the permissions of the user, etc. And we can also do this process for the different values within the feature. This would give us eventually a mathematical model, a basic linear model. And once we have this model, we can assign score to the different transactions and eventually prioritize the transactions by these scores. Well, it's a very, very good method, and it's been proven to get to the way that the security officer thinks and to these priorities. However, it is constant. So if there is a change in the policy, we have to do this over and over again. So we have to redo it. It does not learn. So naturally, we'll say, okay, we want something that learns. We can try pairwise ranking or listwise ranking, or another name, supervised machine learning. As I said, pairwise ranking is much easier than listwise ranking, because when I ask you, if you go into the ice cream shop and I'll tell you, okay, can you rank all the flavors? Then it's really a hard job. But if I ask you, what do you want more, vanilla or chocolate, then it will probably be easier to answer that question. So we are taking a pairwise approach. We're getting as an input a pair of objects or 2 queries. And as a result, we get a rank pair. We say, okay, this is riskier than the other. Because it's transitive, then we can eventually prioritize the entire list. And we can use for that established algorithms like ranking SVM or rank boost or RankNet or any other ranking known method, which is great, but it has a really big drawback. It's a really huge drawback, especially in my case, but I guess everyone gets this drawback, that we need a lot of data to train and we need it to be annotated, right? So, well, I come to spread my system and I tell the security officer, I can make it really like to your likings, but first you have to rank for me 1,000 queries and tell me which is riskier than the other. And I don't really know how well you know this security systems, but until we get to the part that we're discussing the ranking of the alert, they have to do so much work. They have to define user groups and a lot of, and build many rules and the policy, etc. So by the time they get to the ranking their alerts for their liking, to make it easier for them, they don't realize, like, they would say, oh, we don't want this system anymore. So we can't really ask them to annotate this data, which leads us to our solution. We call it CyberRank, and it's actually it's a combination between the two other solutions. We start with AHP, which is a simple process, takes a short amount, like half an hour or so, and we get an initial model. With this initial model, we can do two things. One, we can generate synthetic examples, and we can annotate, and if we have data, if we already have data that is collected, we can annotate it, tag it, label it, so that we get an initial model, which is better than random, and once the user starts giving us feedback or is willing to annotate examples, we can combine them for learning. So the model looks like that. We have the expert knowledge there. I don't know if, I don't know. So we have the expert knowledge there. We model it into a weighted model. We use this model to generate synthetic annotated examples, and we add it to the database of the examples. We can also ask the user to, if he's willing to participate, to annotate a small amount of examples, and we take the entire examples database to build the initial machine learning model. Once we have the machine learning model, then we can rank the list, and we can collect the feedback from the expert back into the database, and relearn and do active learning. Also, this process has the advantage, if we have a change in policy, or we discovered a really dangerous breach, then we can quickly change the model, retrain the model without a lot of work. So I'll show you some examples, or I'll show you the results. This graph shows, especially the cold start problem. The x-axis shows us how many examples we have, annotated examples, and the y label shows us the accuracy of the model to the priorities of the users. And we can say, and we're starting from 10, because below 10 we can't really build any model, machine learning model, but if we use AHP, we can do it from zero, of course, zero examples. And we can see that this black line is our model, the gray line is the machine learning rank SVM, and the this blank axis line is the AHP. And we can see that in the cold start scenario, when we have very little examples, then the CyberRank outperforms the ranking SVM. But as we go along, it's not falls of the ranking, the machine learning. So we get the advantage of getting better results at day one, and then keeping the accuracy of the model. So it's better to use it. Okay, so now that we know how to annotate our examples, we can actually leverage them for sampling. As I said, we have the big data. It's fed into the anomaly detection. And I would like to discuss about the smart sampling, or why should we sample. So let me start with reminding you our motivation. In the YMO against Uber's lawsuit, the data that was discovered, the breach was not discovered because of the anomaly detection. The anomaly detection it wasn't the reason why the whole thing started. Someone snitched. But they could prove it because the data was monitored. So monitoring or collecting the data is value on its own. So what should we collect? Or we can't really collect everything. So first, let me tell you about why can't we log it all? So we're talking about hundreds of thousands of transactions per second. That amount of data it's impossible to log it everything. So we have a limited capacity, and the capacity will decide for us which data would be sampled, and so that's the how much. But who decides the why? The why is decided either by the regulator selling what we should monitor and for how long, or by the security officer who is in charge of keeping our organization safe and deciding what's hazardous or not. How do they do that today? Well, they're mainly using user groups and data risk groups, and they have a list of rules which are manually defined. And we would like to help them and take this load out of their back. But what I'm telling you today, I'm talking about the security domain, but it's not limited to big data. So if it's applicable in other problems. So if you have to collect data, and every piece of data costs you money, if you have sensors or you have to pay someone to sample your data, then you're probably sampling. So if you're sending a salesperson to cold call a prospect, you can't really call the entire population, and so how do you decide who to call? That's sampling. Or let's say in Flint, Michigan, they had a problem with lead pipes, that they were very dangerous for the population. But how do you know which building has a lead pipe? It's not mapped. So in order to find out where there are lead pipes, you have to drill, and the drilling is really, really expensive, and it takes a lot of time. So you have to have a policy for where to drill and where not. They used to have a policy that decided that you would drill in all buildings that were built during the World War I or II, or either of them, which was not accurate at all. They found out that actually the buildings from that time were not carrying lead pipes. And data science for social goods offered a competing model, which was better, but for political reasons, they lost. But anyway, it's sampling. So back to our problem. As I said, policies are hard to tweak. It's a manual job. It's a very, very tiring job. And due to the manual effort, it's rarely changed. So once you have a policy in the security systems, it's rarely changed. We would like to offer another approach so that it will be a more dynamic and it will evolve with the risks. Also, the security officers, when they are defining this policy, they are taking an approach of monitoring the hazardous, the most hazardous users, right? The users that are suspected to be more dangerous. So if you're only looking at the dangerous users, you're only modeling a dangerous activity. So you're biased to this activity. And you would only know, and if you see a regular user randomly, then you would really not know what's normal for him or not, or her or not, right? And also, let's take, for example, we have this Lewandowski dude that was the leading chief engineer of YMO, and he was really exploiting his permissions. How would you know that it's not normal for him to download the entire data spec if you're not really monitoring him from time to time? So I hope I'll convince you that sampling is needed. And when I was thinking about sampling and I was writing the article, I realized that sampling is really actually very similar to the multi-arm bandit problem. What is multi-arm bandit problem? I don't know how many of you heard about the multi-arm bandit? Do I need to talk about it or not? So for the few that don't know, I'll say it briefly. It's basically the problem that you're standing right in the middle of a casino in Las Vegas in the slot machine room, and you have to decide you have a bucket of coins, and you have to decide which slot to use in order to maximize your reward. So our problem is actually quite similar, but mathematically not so much, that we have to decide for each time frame which list of users to monitor in order to maximize the risky activity that is documented and monitored. Well, if you're interested in that, it's partially published in a book that was recently, in a book chapter that was recently published, and it's also under review for, the whole work is currently under review. But I want to show you some, I want to show you some results. I still have time, so I can talk a little bit about why use multi-arm bandits. Well, it's a very elegant approach to solve this problem. And what I discovered in my work, I can show you in the results. Here we have the results of actually real-life data from the air quality monitoring domain. And we can see that we have the policy which is the rule-based policy. That means if we have only 10% of capacity and we can monitor only 10% of the data that we have, because spreading sensors is expensive, then we can see that if the security officers know or the expert knows his data, then it's really actually not that bad. It makes sense to use this approach, that we're using this approach. It's not that easy to beat. But if the security officer or the expert doesn't have the perfect knowledge, does not really know that well what goes on there, then we can see that that if we are using the epsilon greedy approach that we suggest, it outperforms it, and it's robust even for the random beginning. What I would like more to say about it is, like, we would like to support the user and not to replace him, but to empower him and make him happier about the system and help the system help him do his job. So thank you very much for listening.